Okay, this next lecture will be on Newman projections. What I want to do is start pretty simple with Newman projections and just look at propane. Propane, of course, is a 3-carbon chain. And here we're specifying that we're looking down the carbon-1, carbon-2 bond in propane, and I've labeled those carbons on our propane molecule. Many times it's helpful with the Newman projection to go ahead and fill in all your hydrogens, especially those around the carbons specified, so carbon-1 and carbon-2. Everything else that's bonded to the structure, depending how complicated it is, you might just leave it alone in its skeletal form, or perhaps fill in what that group really is. In this case, there's a methyl group there, a CH3. Now, what we want to do is envision what the molecule is going to look like if we were staring straight down this carbon-carbon bond. And I've drawn a bunch of possibilities. These will be our scaffolds that we'll use to fill in. One possibility is always going to be a staggered conformation. The other possibility will be an eclipsed. For most molecules, they'll have several different staggered and eclipsed conformations, all at different energies. We have to be able to predict what's going to be the most stable and what's going to be the least stable. And really, you should be able to know everything else in between. The most important ones will be the most and least stable. So we'll go ahead and start drawing some of these. If we look, the first carbon, the front carbon here, carbon number 1, is only bonded to hydrogens, besides being bonded to carbon number 2. And so on our front carbon, for all of these structures, we'll just have hydrogens. Now what you should try and do is go ahead and fill in the rest of the possible structures for propane that we can come up with. I'm going to start by drawing in staggered conformations. If we look at what's bonded to carbon number 2, we can see 2 hydrogens are bonded to carbon number 2, and then this methyl group. And so I can place those really anywhere, because this is constantly rotating around, and in reality they can be anywhere in these positions. And so that's one possibility for a staggered conformation. Here's another possibility for a staggered conformation. Now notice, because propane is a pretty simple molecule, these two conformations are identical in energy. They're both of the same stability, because the only things bonded on the periphery here are hydrogens, which are very small. Now if we draw eclipsed conformations below, again, this is where the groups on carbon number 2 will be directly behind the groups on carbon number 1. And so there's going to be 1 methyl group and then 2 hydrogens. And so by far the worst interaction will be this eclipsed methyl group with the hydrogen. But in any eclipsed conformation, you're going to see that. And so, for example, we can draw another eclipsed conformation over here. Now the methyl group is rotated down and is directly behind this hydrogen on carbon number 1. But these two projections reveal structures that are of identical energy. They both have the same situation. We've just rotated those carbons. And so there's not much to gain from these structures, but just to show you how you would draw a Newman projection of propane. Well, let's make it a bit more complicated and look at 1-bromopropane. If you can, pause it and try and fill in some structures. Notice, like in the first example, I didn't draw all of the possibilities, just a select few. Any more and it would get a little redundant. Here we want to try and make sure we can represent the best staggered conformation, and then one that's not the best staggered conformation. And then we want to see the worst eclipsed conformation, and then one that's not the worst eclipsed conformation. But we'll be able to see a difference here. So go ahead and try. Again, carbon number 1 is right up front. The circle will represent carbon number 2 in this structure. So we can see that bonded to carbon number 1 is a bromine, and then of course 2 hydrogens. Bonded to carbon number 2 is again a methyl group and 2 hydrogens. And so for all of our Newman projections using this skeleton, they're all going to look like this for that front carbon, and we'll just modify the back carbon to figure out the rest of the possibilities. And so this will be our basic setup. First, I'm going to investigate staggered conformations, which are always more stable than eclipsed conformations. And so on the back wheel, I have 2 hydrogens and a methyl group. Here's one possibility for a structure. And here's another possibility for a structure. Now these two are not of the same energy. Our 2 large groups here, or our non-hydrogen groups that are going to take up more space and be more likely to bump into each other as the molecule's rotating around. These 2 groups are in fairly close proximity. That's called a gauche or a gauche interaction. And that means they're actually going to bump into each other a little bit in that conformation. And that's bad for stability. If we look in this conformation, the 2 large non-hydrogen groups are completely opposite from one another. That's called the anti-conformation. And this will be the most stable conformation. It's more stable than when you have a gauche interaction. Now down here, we'll draw eclipsed possibilities. At the top, there was another one perhaps you drew that had a gauche interaction where the methyl group would be over here and the hydrogen over there, and it would be identical in energy to this one. Down here, when we draw our eclipsed, again, we can draw one where we have a hydrogen directly behind the bromine and then a methyl group directly behind the hydrogen. Or if we rotate that wheel, there's the possibility where the 2 largest groups, the bromine and the methyl group, are eclipsing one another. And this will be the worst situation for the molecule. And so this would be our least stable conformation. These are both eclipsed conformations, but this is the least stable since the largest groups are right next to each other and they're going to have a lot of steric issues, bumping into each other, or molecular friction. But these represent all the different possibilities you could get, or possible energy states in terms of conformations that you would get from this molecule. Next, we want to extend this one further and look at 2-bromobutane. We'll focus on the carbon 1, carbon 2 bond, but we're going to see there's only 2 possibilities because carbon 1 only has hydrogens bonded to it. Outside of being bonded to carbon 2. Carbon 2, however, now has a bromine bonded to it, a 2-carbon chain, and a hydrogen. And so this is how you would fill in 2-bromobutane if you were directed to look down the carbon 1, carbon 2 bond. The outer circle represents carbon 2, and so we can draw an a staggered conformation. So carbon 2 is bonded to a hydrogen, a bromine, and then this ethyl group. We can represent an ethyl group here simply by drawing CH2, CH3. And now you can always count your carbons to double check. We should have 1, 2, 3, 4 carbons represented in our Newman projection. The front here represents carbon number 1. The circle represents carbon number 2. This would be carbon number 3 and carbon number 4. So I'll put carbon number 2 in parentheses since it's hidden from view and it's only represented by that circle. This would be the only staggered conformation you could come up with. Since the front carbon has all hydrogens, no matter how you would rotate this, they would all be the same energy. Likewise, we would only have one eclipsed conformation. And there's different ways to represent this. This whole thing could be flipped upside down. That would still be correct. What's mainly important is the specific interactions you show. A hydrogen eclipsing an ethyl group and a hydrogen eclipsing a bromine. No matter what you draw for an eclipsed conformation, you'll see those two interactions for this specific designation. Moving on from that, we want to look at the same molecule, but now from a different perspective. So we're still looking at 2-bromobutane. But now we want to look down the carbon 2, carbon 3 bond and see what you can come up with for different Newman projections that represent different energy states. I've drawn in the hydrogens on my carbons 2 and 3 to help me out when I go to draw the Newman projections. You can always start with the same scaffold. We'll start with these two skeletons. Now, since we're looking down the carbon 2, carbon 3 bond, that means that this will be carbon 2 in the structure, and the back one will be carbon 3. Whatever is designated as the bond you're looking down, the first one will be the front carbon in the Newman projection, or this position. The next one will be the circle, or the hidden or back carbon. And so if this is carbon number 2, we see that that's bonded to a methyl group, a hydrogen, and a bromine, in addition to being bonded to carbon number 3, represented by the circle. And so we can just fill those in. We have a hydrogen, a bromine, and a methyl group. And I'll fill in the same exact thing to represent another energy state. First, I'll look at the staggered conformations. And so we look at what's bonded to carbon number 3, and the possibilities are a methyl group and 2 hydrogens. So now we have to think, where are we going to put that methyl group? If we're trying to consider all the possibilities, then we can just put it anywhere as a starting point, and then we'll rotate it around to look at the other possibilities. So if it's in this position, we'll rotate it down to here to look at that possibility. And then there's really one more that's going to be a different energy. same front. We're still looking at a staggered conformation. But now this one's yet a different energy. And so let's analyze these different projections. One thing to know when you're looking at these, even though bromine is really heavy, it's just one atom. A methyl group is actually much bigger in three-dimensional space than a bromine. It's not as heavy or dense, but because it has hydrogen branches projecting out, it actually takes up more space. So a methyl group's bigger than a bromine, and we want to apply that to thinking about these interactions. Well, in this particular structure, we have one gauche interaction between a methyl group and a bromine, or two larger non-hydrogen groups. In this structure, we've got a gauche interaction between the methyl group and the bromine, and a gauche interaction between two methyl groups. In the last structure, we have just a gauche interaction between two methyl groups. And so the fewer gauche interactions, the better. And so this would be the least stable staggered conformation. And so even though it's the least stable, since it's staggered, it will still be more stable than any eclipsed conformation. But then we want to compare these and think about the size of the groups. If a bromine is not as big as a methyl group, then the gauche interaction between a bromine and a methyl will be less of a problem than the gauche interaction between two methyls. Since these two groups are bigger, they're going to interact with each other more in a bad way than these two groups here. And so with our one gauche interaction, it's not as big of a problem as this gauche interaction. We would call this the most stable. And it's the most stable overall because it's staggered and it has the least problematic gauche interaction. Now go ahead and try and consider the eclipsed ones too, and you should find you have several possibilities, and I'll do that situation next. So we can set up our scaffolds the same exact way with the same exact groups on that front wheel. And now we'll just think about the groups on the back wheel. And really we're just focused on the methyl group back there. The hydrogens really aren't the center of our focus. And so we can have the possibility where the methyl group is here, and then that means the hydrogens are over here. We could have the methyl group here, or we could have the methyl group down here. And so now we have three different energetic conformations that we can consider. And the same methodology we used here can be applied to these eclipsed conformations. So when we have our two methyl groups in very, very close proximity, eclipsing one another, that'll be the worst situation. Those are the largest groups, very, very close to one another. And so this will be the least stable overall. Now all of these eclipsed conformations are less stable than the staggereds. But when we analyze our other conformations, this would be the best eclipsed conformation that we could see, because all of the big groups, no matter if they're on carbon number 2 or carbon number 3, are just being eclipsed by a hydrogen. And that's the best case scenario. Here, it would be in the middle because we have a large methyl group and then a relatively large bromine having an eclipse interaction. But this gives you a systematic way to predict Newman projections, and you can analyze the most stable and the least stable for really any molecule. And you're just focusing always on what's designated in the problem.